So infinite series are a whole lot of fun, but there's times when you just want an approximation. So a Taylor polynomial says go out to where x is to the fourth, so that's actually the first 5 terms. Go out to where x is to the fourth and just use that fourth degree polynomial as an approximation for this function. So if we're going to find a series for this, we need the first, second, third, and fourth derivatives, and for all of those, substitute a is equal to 1. The other way to do it is if you know a series that can be manipulated to look like this function, then you could use that manipulation. Well, let's see. Could we do the straightforward approach? So you first of all substitute 1, since it's given that a is equal to 1. Substitute 1 into the function, we'd have the natural log of 1, which is 0, divided by 1. So that was easy enough. We would then need the first derivative, which is going to require the quotient rule. So take the derivative of the natural log of x and leave x, the denominator, alone, minus the derivative of the denominator is 1, and then the natural log of x, and then square the denominator. Or in other words, this is 1 minus the natural log of x over x squared. And then substitute that a is a 1. So it's going to be a 0 right here, so that leaves a 1 in the numerator, 1 squared, so we get the number 1. Not so bad. Then we need the second derivative. So again, the quotient rule, the derivative on top is going to be, this will be negative 1 over x times the x squared left alone, minus, now take the derivative of x squared and leave the 1 minus the natural log of x alone. And then square the denominator. So that will be, let's see, when you reduce that, that's just negative x. This is negative 2x, so you have negative 3x's. Then you have to distribute, and it's going to be plus 2x, natural log of x. Oh, we could even get rid of an x. So actually that's negative 3 plus 2 natural log of x divided by x to the third. Alright, then substitute that x is a 1. This again is going to be a 0, so we're left with negative 3 divided by 1. Look at that. We're almost there. We only need up to the fourth derivative, so we need the third derivative. Okay, here we go again. Quotient rule. Well, by now I'm wondering, isn't there some other way to do this? Is it possible that there is a series for the natural log of x, and I could just borrow it, divide by x, and use that, rather than reinventing the whole thing? Well, for natural log of x, so we'll just take a break right here, say, or you could use this series for natural log of x. I don't have on our little cheat sheet, but natural log of 1 plus x is x minus 1/2 x squared plus 1 over 3x cubed minus 1 over 4x to the fourth. And so if we're going to use the fourth degree Taylor polynomial, we just need up to that point. Then this one has 1 plus x, and we need to get rid of that. So if I were to replace x with x minus 1, then I just need to do that here, 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 and here. Then the negative 1 and the positive 1 will cancel, and that would work. So we'll have the natural log, and then this, the 1's cancel, you just have the x. But then I have to replace this with x minus 1, etc. There we go. And this one says divide by x, so if you divide by x on both sides, there it is, my fourth degree Taylor polynomial. That was a lot easier than the derivative stuff. I then need to check the answer and say graph this. When you're close to 1, the two graphs should look the same. So y equals the natural log of x divided by x, so close to 1. So -1 to 3 or so. Yep, that looks like the natural log function. And now this polynomial. So x minus 1 divided by x, and then minus a half, and x minus 1 is squared divided by x, because I don't need parentheses, and plus 1/3 x minus 1 is to the third divided by x, minus 1/4 x minus 1, and then divided by x. Oh no. Oh, I see. Come on, little calculator, you can do it. My calculator is graphing them both at the same time,